And welcome to the next edition of our educational webinar program, Extreme Copper and Heavy Copper PCB Capabilities. As many of you know, we're in our 61st year of supplying the leading OEMs and contract manufacturers in the electronic industry as a high-tech provider of printed circuit boards, cable assemblies, user interfaces, and custom battery packs. Our 110 worldwide employees are here to work with our customers on improving their designs, reducing your time to market, and taking out unneeded costs. Before we get started today, please note that everyone is on mute so that we can best control the audio quality. Therefore, if you have a question, please type it in the question box, which is located in the bottom corner of your GoToWebinar screen. At the very end, we will pick a few questions that will be answered, and all the questions will be answered via email within the next day or so. Our presenter today is Dave Basista, who is Epic's Heavy Copper and Extreme Copper Product Manager. With over 29 years of experience in the power electronics industry, he brings a wealth of knowledge to this topic. Most recently, Dave was the president of UPE Inc., a company that Epic acquired where he pioneered the design and manufacturing of printed circuit boards from 20 ounces all the way up to 200 ounces. At this point, I'd like to turn it over to Dave, and he'll take you through the technical issues that we came to talk about today.
Thank you, Ed. Thanks for the kind introduction. Good afternoon, ladies and gentlemen, and thank you for taking the time to join us for this webinar covering heavy copper and extreme copper printed circuit boards. We have quite a bit of information to cover and really not enough time for everything in great detail. So I'll try to cover this from a broad sense. I will be available to answer the questions at the end as Ed indicated. Without any further delay, I give you heavy copper and extreme copper printed circuit boards. So we'll start off the presentation. I'll cover the definitions of a few terms we use, then jump right into application requirements and design considerations. We'll follow that up with a brief summary of techniques we use to create these circuits. Then I'll provide a portion of our tables used to estimate the current carrying capacity of heavy copper or extreme copper tracks. The tables we provide are for DC current. We also touch on DC versus AC and how that affects current capacity. From then we'll get into the details regarding the minimum line width and spacing for various copper thicknesses. We'll also talk about heavy copper, plated through holes, and vias for maximum reliability and advantages to connector sites. And to round out the topics of this presentation, we'll touch on the role of extreme copper in thermal management, and finally the use of heavy copper in power planar magnetics. We define standard copper as 1/4 ounce to 4 ounce per square foot. Heavy copper is 5 ounce up to 19 ounces, and extreme copper is 20 ounces up to as much as 200 ounces. Now, while 200 ounces may not be practical or even necessary for most applications, it is a real option. In this picture, you can see an example of extreme power link. You can see 2 ounce copper pads on the surface for surface mount components, as well as some larger extreme copper square pads. This board was bisected in both the X and Y axis to reveal the extreme copper tracks contained within the board. Those large square pads are solid copper from the top surface to the extreme copper internal tracks, and then through to the bottom of the board. The internal tracks that you see here are just under 100 ounces. Going to such an extreme construction didn't happen overnight. I spent about 3 years testing and refining many proprietary processes before finding the right solution that provided the precision, performance, and reliability necessary for mission-critical systems used by Tier 1 defense contractors today. So for an experienced extreme copper fab shop to assist the designer in their efforts to take advantage of these capabilities, we'll need to understand a few things about the application requirements. Key elements we'll need in order to offer recommendations are dimensional limitations, layer count, current requirements for power tracks, current requirements for plated through holes, material or temperature requirements, connection options for signal and power, and types of components used, whether it's surface mount through hole or screw terminal. So getting into design considerations, now the designer will need to weigh the trade-offs relative to price versus performance and reliability. Minimum line width and spacing is dependent on the process used to create the circuit. Plating up allows for finer lines and spaces than etching down, but it comes with a higher cost due to the extra process steps and time required in the plating tanks. A detail that sometimes doesn't receive enough attention is the current capacity of plated through holes. Plating heavy copper in the holes and vias can be essential to ensuring maximum reliability. With boards going through a minimum of 4 thermal cycles during fabrication and assembly, and 2 more cycles for each component repair, a standard 1 mil plated hole begins to weaken and fractures in the barrel can start to set in due to the stress of differing rates of thermal expansion between the copper and the substrate. Plating 2 ounces or 2.8 mils in the barrel dramatically improves reliability of that plated through hole. Power link versus segregated layers. What I mean by this is the option to place multiple copper weights on the outer layer to accommodate both the control circuits and the high current circuits, as compared to keeping the control circuits on their own layer and the extreme copper for the high current circuits on its own layer. PowerLink can offer a lower mass option by reducing the layer count, making for a thinner overall board. However, this comes at a premium and is typically only attractive to military or aerospace applications where a high value is placed on performance, power density, and reliability. The last point for this discussion is the stack up. For multi-layer boards, we generally try to keep the cores as thin as possible, typically 5 mils, in order to allow more space for pre-preg separations. As we press the extreme copper or the heavy copper in inner layers, we have to make sure that there's plenty of pre-preg to fill the open areas between the tracks. The pre-preg needs to be about as thick as the total copper thickness of the adjacent layers. For example, we would want to see 28 mils of pre-preg between adjacent layers of 10-ounce copper. Adding a little detail to the previous slide, here we have a simple sketch depicting the cross-section of a track created by the way of plating as compared to starting with full copper thickness and etching away the copper in the spaces between tracks. You'll notice that the additive process produces a very well-defined track, allowing for finer lines and spaces. Alternatively, the etch track has a trapezoidal shape and is less precisely defined. It requires larger tracks and spaces, but it is more economical. In this slide, we simply use the IPC formula for current capacity of an external track to populate a spreadsheet giving us the estimated current capacity of various copper weights and at a variety of track widths. In this chart, we set the temperature rise to 20 degrees C. Excuse me. So to get a quick gauge on how much current a half-inch wide track can carry with 14-ounce copper, we can look to the chart and find 140 amps. And a 125 mil track with 45-ounce copper can handle 120 amps. You'll notice that if you are designing with some wide copper planes of 1, 2, or even 4 ounces wide, the current capacity quickly reaches previously unthinkable levels for a printed circuit board. Keep in mind that these values are for external layers. We recommend derating internal layers by 50%. For AC circuits, we have to consider skin effect. As probably everyone knows here, the current carried by a conductor in an AC circuit carries that current primarily on the surface and is frequency increases, the skin depth decreases. So for a circuit switching at, let's say, 10 kilohertz, the maximum effective thickness is 37 ounces. And at 100 kilohertz, the maximum effective copper thickness is just under 12 ounces. So we can take the 37 ounce and the 12 ounce effective copper thickness, refer back to the current capacity chart, and find capacity for those tracks. So for example, 12 ounce copper with a 250 wide track, it will carry 76 amps. If we had used 20 ounce copper and at that same frequency, the maximum current would still be about 76 amps, because anything above 12 ounces is essentially wasted copper. On to line width and spacing. Line width and spacing is an important limitation to understand as we move up the scale to heavy copper and extreme copper. So we created this chart which provides limits for minimum line width and spacing as a function of starting copper weight and finished copper weight after plating. A simple rule to remember is the absolute minimum line width or space cannot be less than the copper thickness. So for 10 ounce copper, the minimum line width and space can be no less than 14 mils. And this is only achievable when we are plating up from quarter ounce or half ounce copper foil. If we're starting with more copper and plating less, we have to allow for etch back and compensation, and the minimum line widths and spaces grow larger. As previously mentioned, the amount of copper applied to plated through holes is a critical factor in the overall reliability of the board. There are two key elements to consider. The first is the current capacity of the barrel for an acceptable heat rise, and the second is the mechanical strength determined by the copper thickness, hole size, and whether or not there's any support vias. In this slide, we'll look at the current capacity. I found that, for me, the easiest way to calculate the current capacity is to think of the barrel of the plated through hole as a track wrapped around a tube, or wrapped into a tube, rather, where the width of the track is equal to pi times the diameter of the hole. We can then use that value to go back to our chart for current capacity and find the current that matches the amount of copper plating in our hole. So if we consider a 40 mil hole times pi, we find a track width of about 126. Looking back on our chart here, this will give us a rating of about 20 amps at 4 ounces of copper, or say 40 amps if we're using 10 ounces of copper in that hole. We can perform the same calculation for each of the support vias and add the capacity of each via to the plated through hole to determine the total current capacity of the plated through hole and support vias. The circuit board industry has developed a test method for determining the thermal integrity of a finished circuit board. It entails the use of a circuit of 32 plated through holes where the tracks alternate between top and bottom of the board and are stitched together through the plated through holes. Thermal studies done on standard FR4 material have shown a 32% failure rate when plated with 1 mil of copper and exposed to 8 air-to-air thermal cycles, going from 25 degrees C to 260 degrees C. Failure is considered to be a 20% increase in resistance. Increasing the plating thickness to 2 ounces or 2.8 mils of copper, that failure rate drops to 0.57%. Let me repeat that. Increasing the plating thickness to 2 ounces or 2.8 mils of copper, that failure rate drops from 32% to 0.57%. The importance of thicker copper in the plated through holes is crystal clear. The use of heat sinks for board mounted components has been commonplace for as long as printed circuit boards have been around. Anything from the crude penny and paper clip, as pictured to the right, to the more effective extruded aluminum or water-cooled cold plate, pictured lower left, are typical methods to keep components cool. By adding copper to the outer layer of a PCB, we can add additional cooling support to the board and the components mounted to the board. Pictured in the box, heavy copper or extreme copper can be plated to selective areas, which will act as a heat sink, drawing heat from within the board. The plated copper may be enough to support the cooling requirements in itself, or it can be used as a direct interface to an extruded heat sink or cold plate. This same concept would also apply to extreme copper. And the image at the bottom right is that image indicating the heavy copper selected area that would support the cooling. I'm pretty sure everyone is familiar with planar magnetics. It's not unusual to find them embedded into a PCB, only requiring the core to be made functional. Alternatively, discrete units are an industry unto themselves. The unique capability we can offer is high layer count, fully encapsulated, single board solutions which offer high precision and repeatability. They can be made with thin cores and separations with very high reliability and offering excellent turn-to-turn and layer-to-layer isolation. Our customers have said that this construction also provides for superior partial discharge performance due to the dielectric strength of a fully encapsulated multi-layer PCB construction. While EPIC does not design planar magnetics, we are uniquely positioned and experienced in producing boards for this application. Thicker copper options, high layer count, and heavy copper plated through holes are key to a high performance and highly reliable planar transformer. With this, I'll kick it back to Ed. Talk a little bit about the products.
Great, thanks, Dave. As you're reviewing the questions, and we pick a couple of them to answer here. As we talked about, EPIC has been a printed circuit board manufacturer for over 61 years. Along with that, though, we also build and design custom battery packs, Plex and Rigiplex printed circuit boards, user interfaces, including high reliability keyboard assemblies with our new AS9100 facility that we just acquired, Suncoast Digital in Largo, Florida, fans and motors for the commercial refrigeration and HVAC industries, and high reliability cable assemblies that, again, are built in our AS9100 factory in Largo, Florida. As we talked about today, we have design and technical support in all of our products. So we have people just like Dave who are experts in their subject matter available at any time to help all of our customers with their design issues, any technical support needs that you may have, and to actually help do some testing if required. So please utilize these folks. It's that we're here to help you make your designs better, more cost effective, and get you to market faster. So thanks all for coming today. I'm going to turn it back over to Dave and let him answer a few of the questions that have been asked.
All right. Thanks, Ed. I have a few questions here that are good questions that I think we should share with everyone. The first one is, what are the advantages of using something like a 12-ounce copper layer rather than paralleling 4 layers of 3-ounce copper or even 4-ounce copper? I can think of a couple advantages. First, by eliminating parallel connections, we can be sure 100% of the current will flow through that one layer, which is important because when layers are connected in parallel, the current usually doesn't share equally among the parallel paths, which leads to higher temperature rise in some of the layers than expected. Secondly, even if the temperature variation is acceptable, the board will still require heavy copper plating in the through holes, or possibly heavy copper vias added to handle the current through the board without a concern for failure. EPIC can provide fewer heavy copper or extreme copper layers and the necessary through-hole plating to ensure maximum reliability. Second question, how are components soldered to a thick copper printed circuit board? And this is a good question many people ask. because assemblers sometimes have problems or concerns about this. And really, I can say a couple things here. If components have to be soldered directly to thick copper pads or through holes, the assembler will need to run some tests to identify the best profile for the job. But in general, we say that the boards will need to be preheated for an extended period of time prior to the assembly. These boards can have a lot of thermal mass, so a lot of care must be taken to make sure the board is heated all the way through prior to soldering. Alternatively, we could keep the solder pads and through-hole components in thinner copper, like 2 ounce for easier assembly, and only the power connections will have the thick copper applied. The power connections are oftentimes made with fasteners, which don't require soldering. Let's see, last question I have here. What types of connections can be used for high current in and out of the printed circuit board? Well, there's many options available on the market. Components obviously have their connections defined by the package. And for high current components, the connections are typically screw fasteners or threaded studs. Similar connections are made with cables using ring terminals, which can be attached with connectors that press into the board, something like a PEM nut or a PEM stud. There are also pin and socket or blade type connectors that are available, and those are useful for blind insertion or hot swap type of applications. A quick Google search will produce many options. But if you need any recommendations in this regard, we're here to help you and offer any direction that we can. So that is wrapping up the questions that we have time for today. Any other questions that I didn't get to, we will be responding to that in the next day or so, as Ed indicated initially. So thank you very much for joining us. Appreciate your taking the time, and we look forward to seeing you at the next webinar from EPIC.